Hello and welcome to lesson 7 in this series on metric and topological spaces. In this lesson we're finally going to get to the key idea, which is the topological space. And as always, in the description are links to recommended textbooks and the booklet for you to follow along and do the exercises in. So everything we're going to see today were theorems we proved when we're looking at metric spaces. They're now going to become definitions in topology. So topology, in a way, extends from the notion of a metric space. It's a bit more general, and we'll see can still do a lot of the same things. So what actually is a topological space? So a topological space, X tau, consists of a set X and a collection of subsets of X, which we call tau. The elements of tau are called open sets, and they obey the following three premises. So firstly, both the empty set and X as a whole are both elements of tau. Secondly, given a finite collection of open sets, so that's elements of tau, the intersection of all of these is in tau. And similarly, given in this time an arbitrary collection of open sets, the union of all of these is again in tau. So that is, it's closed under finite intersections and arbitrary unions. Remember that we proved this for open sets in metric spaces. So we've taken that theorem from last lecture and turned it into a definition. And note that when we say open sets, we do just specify what they are. Sometimes there could be a rule or a good reason, but at this level we're just specifying what tau is, so what the collection of open sets are. They just have to obey these three rules. And then, as before, a set is closed if its complement is open. So again, just as before. Okay, let's look at some examples. So our first example is going to be for a finite set. So in this case, we take X to be 1, 2, 3, and tau to be the empty set, X as a whole, then the set 1 and the set 2, 3. So this is not the only topology, but we're just going to use it for this example. And then we're going to use this example again throughout the video and throughout the homework. Okay, so we need to check that this is indeed a topology. So firstly, well, yes, the empty set and X are both open. Now, in order to check the intersections and unions, we're just going to do a few and show that they're still in there. So I would say pause the video, try a couple of intersections and unions of open sets, and then just see that they're open. There's only a finite number you can do. Okay, now you've had a go. I'll just put some examples up. So to check the intersections, you can see we've got X intersect 2, 3 is 2, 3, and that's open. The empty set intersect 1 is the empty set, and that's open. 1 intersect 2, 3 is the empty set. And so on, right? There's more combinations, but you get the idea. Then for C, again, we have to check the unions by hand. Again, this could be an arbitrary union, but there's only a finite number of sets, so we only to do a finite number of them. Again, I've only put up a few, but you can see that all of these unions are again open. Our second example is the discrete topology. So here let X be any set, and then tau is the power set of X. So that is the open sets are just any and all subsets. And this is the same topology we would get from the discrete metric. So here, so with the discrete metric, any and all sets were open. Okay, so to check that this is a topology, obviously the empty set and X are both subsets of X, so they're both open. Then we want to check the countable intersection. So the intersection of any number of subsets is again a subset. So that's fine. It is open. And then have a go on your own, see if you can check for the arbitrary union, and then I'll put up the argument. Okay, now you've had a think. The way we can show that the arbitrary union is also open, well, the union of any subsets is again a subset of X, so it must be open. Our third example is the indiscrete topology. So this is the opposite of the discrete topology. Here, the only two open sets are the empty set and the whole set X. So let's check that this is indeed a topology. So on your own, go through and check the three axioms, and then I'll put up the solutions. Okay, now you've thought about why this is a topology. For the first axiom, well, the empty set and X are in tau, so it's kind of by definition. Then for the intersection, well, the empty set intersect X is the empty set, which is in tau. And then for the union, the empty set union X is X, which is in tau. Our fourth example is the Euclidean, or what's sometimes called the standard topology. So this is let X be Rn, and then the open sets are those such that for any point in U, there is an R greater than 0, such that the open ball of radius R centered at A is contained in U. And remember, to define an open ball, we need a metric. So this is going to be the Euclidean metric, hence the Euclidean topology. Then we need to check this as a topology, but in fact, we already did this in the last lesson. We had that big table proving all of the requirements of open and closed sets. And in fact, we could define a topology from any metric space in a similar way. We don't have to use the Euclidean metric. We just say we take a metric space, then the open sets in that metric space, we can just define a topology using those. And in fact, that's an equivalent definition of the discrete topology from before. Okay, our last example is the cofinite topology. This is quite a strange example of a topology, but it's quite nice for showing how weird topologies can be. So for our set X, we take the real line, and then for our topology, the open sets are those such that the complement is finite, or the complement is all of R. We could define a similar topology for any set actually, but we're just going to stick to the real line for now. Okay, so to check this is a topology, firstly we want to check are the empty set and X in the topology. So we need to check, are the complements of these finite or all of R? So R complement the empty set is R, so therefore the empty set is open. R complement R is the empty set, which has no elements, which is definitely finite, and so R is open. Now have a go on your own, or have a think on your own about the countable intersections and the arbitrary unions, and then I'll go through the solutions one at a time. Okay, now you've had a think, let's have a look at finite intersections. So let U1 to UN be a collection of open sets. Then the complement of this intersection is the union of the complements. That comes from De Morgan's law. Each of these complements contains a finite number of elements, since that's the requirement for them to be open. I've put it in yellow, or if one of these open sets is the empty set, then this is all of R, but then you can check that this makes everything trivial since the union is just all of R. So if that's not the case, then we have this union of sets, each of which are a finite number of elements. However, this is a finite union, and therefore if we're doing a finite union of a finite number of sets, and each set is finite, then the end result also contains a finite number of points. Okay, have a go at the arbitrary unions. It's quite similar. So have a little think and then I'll go through the solution. Okay, now you've had a think. Let's look at the arbitrary unions. So firstly, let UI be a collection of open sets, indexed with a little I. Then we want to look at the complement of the arbitrary union. Well, this is the intersection of the complements. Now, each complement contains a finite number of elements, or all of R, but that doesn't matter since we're intersecting. So if we keep intersecting a load of finite sets, even if we're intersecting an infinite number of times, each of them is finite, so we look at what's in all of them, that still must be a finite number of points. And hence, the arbitrary union is also open. Based on our theorems from before, we can define convergence in a topological space. So if xt is a topological space and xn is a sequence, then xn converges with respect to the topology tau to a point x if for every open set U containing X, there exists an n greater than 0 such that Xn is in U for all n greater than big N. And note that unlike in metric spaces, it's perfectly possible in a topology for a sequence to converge to multiple limits. Consider the topological space from example 1, so that's the finite topological space. Where does the sequence 3, 2, 1, 1, 1, 1, 1 forever converge? Well, looking at this, it's almost definitely going to converge to 1, but let's check. Remember, topologies can be a bit weird. So the only open sets containing 1 are X and 1. So we just need to check, does the sequence remain in these for a big enough n? So the entire sequence is contained in X. I mean, that one's always going to be true. And for n greater than 2, the sequence is also contained in 1. So therefore, for every open set containing 1, the sequence enters and then remains within that set. Okay, for the second example, have a go on your own and then come back to the video. Okay, so we want to check that the sequence converges to both 3 and 2. So we need to look at all the open sets containing 3 and 2, and these are X and 2, 3. There's no open sets containing either 2 or 3. And again, the entire sequence is contained in X. That's fine. Similarly, for all n, the sequence is contained within 2, 3. So for both of these open sets, the sequence stays within this open set. And since this is every open set containing 2, then the sequence converges to 2. Similarly, this is every open set containing 3, and so therefore it also converges to 3. Okay, for our next example, we're going to use the cofinite topology, and we're going to show that the sequence 1, 1, 1, 1, 1 forever converges to 1, but no other point. So the sequence is contained in every set containing 1. So it obviously converges to 1 because every open set containing 1 contains the sequence. The difficult bit is to show it doesn't converge to any others. So let's just look at the point 2. The argument would be the same for any other point. Then the set R complement 1 is an open set containing the point 2. We can tell it's an open set because if we complement that, so the complement of R complement 1 is just 1, and that's finite. However, because this set doesn't contain the point 1, the sequence is never in that set. And so therefore the sequence doesn't converge to any other point. Okay, for our next example, have a go on your own and then come back to the video and I'll go through the solution. Okay, now you've had a think. I'll start off with this kind of hint. So every open set in the cofinite topology is of the form R complement and then a finite number of points. Now let's consider an arbitrary point x. X is in R complement A1 to AK. Okay, we have to be careful that x is not equal to A1 to AK, but we can always, for any x, we can find loads and loads of sets of this form. We can pick loads of different AIs, and as long as none of them are x, x will be in that set. So it's not really a strong condition, this in brackets here. Now, since this A1 to AK is finite, there is a maximum value, which we're going to call A. So A is the maximum value of A1 to AK. Then for all n greater than this maximum value, the sequence is contained in R complement A1 to AK. That's because if n is greater than A, then it's bigger than all of the points we've taken out. So it's not one of the points we've taken out. Therefore, the sequence converges to X. So again, the way we can say this converges, we need to check every open set, but since every open set is of this form, it's fine. And if we didn't have this thing in brackets of X not equaling A1 to AK, X wouldn't be in the set, so it wouldn't be an open set containing X. And then finally, X was arbitrary, so we can do this construction for any point X, and therefore we can show this sequence converges to any and every point. Okay, we can also define continuity for a topological space. So if x tau x and y tau y are topological spaces, and f maps x to y as a function, then f is continuous with respect to the specific topologies if for all open sets u in ty and tau y, the pre-image is in tau x. That is, the inverse of open sets is open. Okay, let f map R to R be given by f of x equals x. We take the domain to have the cofinite topology and the codomain to have the standard topology. Show that in this case f is not continuous. So let's look at the set 0, 1, and this is open under the standard topology. We look at the pre-image of this, and this is just 0, 1 again. Is this open? So we take the complements, and that is the union of these two infinite sets, and hence this is not finite, and hence 0, 1 is not open in the cofinite topology, and therefore f is not continuous. For the next example, we've swapped the topologies on the domain and codomain. In this case, show that f is continuous. Okay, have a go on your own and then come back to the video. Okay, now you've had a go. So we're going to start off by reminding you that every open set in the cofinite topology, obviously except the empty set, is of the form R complement a finite number of points. Again, if it's the empty set, then this is all quite trivial. So we take the pre-image of that, and that is just R complement those same points again. So we want to check, is this open? And we're just going to assume that these AIs are all in order. It doesn't really matter, but it just makes the next step a little bit easier to write out. If they're not in order, you can just rearrange them. Okay, so the complement is equal to the union of all these open intervals. And the union of open intervals is open. And because this R complement A1 to AK is the general form of an open set, we've shown that the pre-image of any open set is open, and therefore f is continuous. The last thing we're going to look at is limit points or accumulation points or cluster points, whatever you want to call them. So let X tau X be a topological space and A a subset of X. So just like last time, there are two definitions of a limit point. So the first one is that a point A in X is a limit point of A if every open set containing A contains at least one point of the set A different to the point A. And the second definition is A is called a limit point of the set A if there exists a pairwise distinct sequence that is fully contained in A and that converges to A. And we're not going to prove that these are the same because these are exactly the same as before. The proof would be exactly the same as it would be for metric spaces. So actually there's nearly nothing new here on this slide apart from the fact that it also holds in topological spaces. Okay, so we're now looking at example 1. What are the limit points, if any, of the point 2? Well, the answer is just 3. The only open sets containing 3 are X and 2, 3. Both of those intersect the point 2. Nice and easy. On your own, in the cofinite topology, what are the limit points of the interval 0, 1? All right, have a go on your own, then come back to the video. Okay, so let's take an arbitrary point, X. All the open sets containing X of this form, they're of the form R complement A1 to AK. So again, as long as we pick A1 to AK such that none of them are equal to X, X is in this set, and this is what the general form of an open set is. So every open set containing X is going to look like this. So then we look at the intersection of that with the interval 0, 1. And this contains an infinite number of points. So how do we know that? Well, R intersect 0, 1 is just the interval 0, 1. The interval 0, 1, even though it's finite in the sense that it's bounded, it contains an infinite number of points in between 0 and 1. So 0, 1 contains an infinite number of points, and then we just take away A1 to AK, so we remove a finite number of them. We're still left with an infinite number of points. And therefore, it contains at least one point that is not X. And therefore, the limit points of 0, 1 are all of R. I mean, maybe you can justify that using the notion of sequences. So you can construct a sequence that fits within 0, 1 and converges to every point. So that would be another way to prove this.